Alright, so everyone, today we're going to talk about this topic called related rates. And related rates deals a lot with the chain rule and using it in clever ways. So consider this scenario here. Assume that the oil spilled from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 meters per hour. How fast is the area of the spill increasing when the radius of the spill is 60 meters? So it's clear to see that as the radius changes, the area is changing. So that's why they are two different rates, and that's why they are related. Okay, and so the way we start off these problems all the time is we write down, keep track of what we know and what we are asked to find. And what I know is that the radius increases at a constant rate of 2 meters per hour. So I know the change in radius, dr dt, is equal to 2 meters per hour. And I'm looking for how fast is the area increasing. So I'm looking for dA dt. Okay, that's what I'm looking for when r is equal to 60. And so that's the first thing I want to do. I want to write down the information I know. And then I want to somehow, I know I want to look for a relationship that relates area and radius. And I know because it's circular that area and radius are related by pi r squared. And I'm looking for dA dt, but there's no t in this formula at all. But what I do know is I know that if I want to find dA dt, I could find the derivative of a with respect to r, and then using the chain rule, do dr dt. And this is exactly what the chain rule says. Okay, we find this. Okay, we've seen the chain rule also when it looks like this, g of x, where dy dx is equal to f prime g times g prime x. But this is another way to think of the chain rule. I take the derivative with respect to r, and then I take the r with respect to t. Well, I do not know dA dt. I'm looking for it. I know this value, and this one here I can actually find. And so if I take this function here, I recognize the derivative. This is, if I take the derivative, and it's r because that's what it's in terms of, is going to be 2 pi r. The 2 comes down, subtract 1. And so dA dt is simply going to be dA dt is going to be dA dr, which is 2 pi r, times dr dt, which I know is from here, 2. And I want to find this when r is equal to 60. And so what I can say then is dA dt is equal to 2 pi times 60 times 2, which if I put that all together is 240 pi, and it is area, and it's in meters, so it's going to be meters squared per hour. Okay, and so this idea of writing out the chain rule, and then with the chain rule, we also want to find the relationship that relates the variables that we know about, a and r, and how it all fits together. And sometimes coming up with this, we have to think quite cleverly, but that is in essence the idea. So we label the quantities we want. That's really important. We actually think very carefully what we have and what we want to know. We find an equation that relates the quantities of the unknown rate, so in the previous example was area, with the quantities that we knew, which was r. This was area and this was r. Then we differentiated this equation using the chain rule, and we solved the derivative of the unknown rate of change. And then we evaluated the derivative as needed. And that is the key to related rate.